We're good to go now. So, yes, Boffin. What do we see immediately, right? So we're printing out, hey, what's your name? Gits. This is a bad thing. We call printf, and then we leave. But you'll notice, like, again, there's no stack canaries in here, right? And we also have this wonderful give shell function. So in this case, this is just a straight up overflow to overwrite the saved instruction pointer with the give shell function. Everything is here for us. All we need to do is just write a lot of A's, write the address of give shell where we want it, and we should be good to go. So let's walk through. Let's see, Boffin, Pi. So I'm going to write all these using pwnables again, just to kind of get everybody, you know, if you don't remember exactly like what pwnables has, this should be like get you familiarized with it again. All right, so again, we need to import everything from pwnables. We're going to create our process called Boffin. We are going to, for now, let's just see if we can do this one statically. Actually, you can see up here we're subtracting hex 20 from RSP. This is after pushing our base pointer, though. So you know our RBP is 8 bytes. So we need to add. We have like RSP is down here, so we need to add the 20 to get back up to where we were here, and then another 8 because that 8 was our saved RSP. So in theory, if we just do p.sendLine of hex 28 A's, and then we need to give it the address, right? This is what's going to be, in theory, overwriting the saved instruction pointer. Again, we have this give shell function. So 40069D. We can also, if we want, create like elf, create the binary in memory inside of pwnables, and then just do elf.symbols of give shell. This is, you know, again, I wouldn't worry about getting too familiar with dot symbols. This will be much more useful when we're getting into a little bit more advanced exploitation where you have like a libc leak and you need to find where some other address is in libc. But for now, this is fine, you know, or we can do it the other way. And then I know a lot of people were confused if they did like gdb.attach onto process, but then if they had these two lines commented out, what you'll see is, not that, you'll get this. Oh, well, yeah, it'd help if I actually made it executable. Backdoor Boffin school. Let's make sure it can run. All right, yeah. So now if we run this without having a pause in there, basically what's happening is the Python code is running till completion because this gdb.attach is almost asynchronous, you can think of it as. So what's happening is the program is being started, and then Python is essentially running until it's done, which is then killing off that process. However, GDB is trying to attach to that process, but that process is now dead. So you'll get this invalid address or something along that sort, something of that sort. Invalid address, couldn't read memory, you know, like the stack stuff. Anything like that, that almost always means something in your Python, like your Python code is crashed, or it's exited, or something along those lines. So we'll make sure that we have that p.interactive. You can also use the pause command, or the pause function. This is another pwnables thing, but in our case, we shouldn't even need that. Python 2 Boffin. So in this case, you can see, all right, well, we got bin dash, so you know we're all set. We have our shell now. So let's exit out of all that. Does anybody have any questions about this script? We can even get rid of the GDB stuff for now. Any questions about how I got constants or the symbol stuff or anything like that? Please don't hesitate to ask questions, by the way. Like you're going to need to know this stuff because, especially with ROP, you're going to need to be creating potentially longer, 20 plus lines of Python to set up all of your ROP chains and that kind of stuff. So like if you aren't familiar with this, you're going to have a bad time later on. Yes? What's the P64 ELF symbol? Yes. Okay, so P64 is just a function that takes a number in and spits out basically the packed version of that. So again, if I just put like the string representation of the address, that's going to be typing like, in this case, give shell is 40069D, so that's going to be typing out like the literal ASCII character 40069D, right? This is not the same as the actual number hex 40069D as it's stored in memory. That is represented as the byte 0x9D, 0x06, 0x40, and then zeros all the way out to make it 8 bytes. So P64 is transforming that number of 4009669D or whatever into that byte representation, so that when the when the computer sees that byte sequence, it interprets that as back to the integer that we expect it to be, not the like byte representation of the ASCII version of the string. Does that answer your question for P64?
So it takes a number and converts it to...
Yeah, so let's... Yep, that's fine. So let's... try to import star, if I can type. So if we have an address, let's say hex 1000, or let's actually do hex lead, that makes it a little bit easier. If we just send this, right, if we just do like stir of adder, that's going to be sending the string 4919. This is, the ASCII representation of the letter, or of the character 4, then 9, then 1, and 9. So this is going to be 4 bytes. However, it's not going to be the 4 bytes that we want. And, the address itself, this is actually only 2 bytes, right? Because this is, like, if we look at this, it fits, there's 1 byte, and then there's the beginning of the other, or the end of the other, I guess I should say. So what we need to do is we need to take this 4919, or hex leet, they're the same thing, just different base, and convert that into basically this. And this is a couple of things. So why hex 37, hex 13? This is basically just saying, instead of writing the literal 37, write the thing that is represented by the byte 0x37. And then same thing for 13. In Python, well, in general, the ASCII version of hex 37 is 7. This is actually sort of a useful thing to know. The ASCII representation of a digit is hex 3 and then the digit. So 0 is hex 30, 1 is hex 31, 2 is hex 32, etc., etc. Yeah.
So it basically converts a hex value into like the little endian representation.
Yes, exactly. And then it's backwards again because little endian, right? So so P64 is doing that, and then symbols is just taking our ELF file, boffin, and if we look at all of the symbols that are exported by it, somewhere in here, where is it? Somewhere in here there is a give shell, there it is, and that's saying basically there is a symbol called give shell that is a function and it lives at this address. And so all e.symbols is doing is just parsing the ELF and then pulling out this address for us, so that we don't have to use Binja and copy it over, we can just use this. Yeah. Any other questions about, any other questions about this? Yeah.
So if you were using elf.symbols, we would have to go into Binja and find the address.
Yes, exactly. So yeah, again, elf.symbols is literally just going to be returning this hex 40069D. So this is equally valid just to do 69D. This will give us the exact same thing if we run this again. There's our shell again. So yeah, it's completely valid to do it this way. To be honest, a lot of the times I'll end up putting all hard code numbers in here instead of using symbols, especially because a lot of CTF binaries won't give you symbols, or the things that you're interested in don't have symbols. So sometimes it is just useful to put consonants in. Yeah. All right. I'm going to interpret no more hands as we can move on. So the next thing we have is school. This case, we don't have a give shell function, right? We still do have gets, which is a good thing to see for us, of course, not for programmers. But what can we do here? So one thing to note is that, let's open this up in GDB actually. If you have pwndebug installed, you can actually do, blanking on the name of it. What, Danny, are you in here? What is the name of it? The just showing information about like NX and all that. I'm just checksec. Thank you. There's checksec command, which will basically show you information about architecture, Railroad, as we discussed today, and more importantly for this, whether you have stack canaries, whether you have stack canaries or NX. NX, as we discussed 2 weeks ago, is the no execute bit, which basically says, the stack should not be executable. This makes sense, and this is how it is by default. However, we've compiled this binary with NX disabled, which means your stack is executable, so you can jump to the stack. And sure enough, we have, we do leak an address here in RAX. And if we run this binary, you can see we do get this schools at hex 7FFF, give me directions. So another useful thing to just kind of have in your mind, I think basically all of the time, libc, don't really care about for now, but more importantly, the stack is almost always going to start with 7FFF. I believe it's actually guaranteed on Linux at least to start with 7F. I forget about the next byte. But if you ever see 7F come back at you, because that's not it's not a valid ASCII character, if you ever see that, that should immediately kind of raise some alarms internally that this is leaking something. Sometimes you'll see it as the hex representation, or sometimes you'll just see it as like a non-printable character. And you'll get used to this very quickly, where that should immediately start to like say, hey, something is not right here. We're either got a leak for the stack or for libc, or something up near like high memory. But yeah, so again, NX is disabled, which means our stack is executable, and we have gets call, so we can just overwrite to our heart's content. So and we have a stack address. In this case, conveniently, it's even the address stuff is read into. We don't have to do any offset calculations. So if let's just Google x64 Linux shellcode. Google is your friend, right? Here's some Shellstorm has some good stuff. I believe this is the exact same that Radari gives you. So if let's school.py, let's get pwntools going again. And if I can hit the right number of things. So we're going to send line sc and interactive. Now, at first glance, this should work, right? Or, well, actually, I forgot a couple things. So let's go back, right? So we have hex 27, or hex 28. Yeah, hex 28 bytes to work with again. We're only using decimal 27 of them, so we need to pad, right? We need to pad our way down to where the return instruction, the saved instruction pointer is. A very common way to do that in Python is you can just do some character times whatever we want minus the length of the shellcode that we have already. And then again, we're going to p64 something, and this is going to be our save. This is going to be where we jump to. But again, where we jump to is not just a function this time. And in fact, if I can type, you can see this is changing, right? So another thing to note here, I guess, is in GDB, sometimes addresses don't change like they do in the real world, which is nice on GDB's end. However, it can mislead you sometimes if you're like hard coding some addresses in place because it's the same address when you launch it in GDB, but that's not true. This is a manifestation of ASLR, which is again what we're going to talk about next week. But at its core, you can see things are changing. So we need to parse this out in our script. There are a number of different ways to parse numbers, right? I'm going to do it the really bad but works way of just string splitting. So in pwnables with processes and with remotes, I believe we mentioned this, but these are just generic. These are basically subclasses of what they just call a tube. And tubes have common methods to get data from them and send data to them, one of which is receive until, which is very nice in this case because we can just say receive until we get this, this colon space that we're expecting. We don't see that anywhere else in the string, so let's just receive until we see that. And then we're going to store this address that we see next. And again, I'm going to be bad and just receive until dot, because again, we see the dot right afterwards. However, receive until actually includes the last characters that it sees, so we need to substring out that last dot. And in Python, for those who don't know, you can do this bracket colon -1, which basically just says give me the substring up until the -1st index, up until the last character. But at this point, though, address is this string. It is the string 0x7ffc6 blah 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 blah, and we need that as a number to pass to p64, right? So again, Python has a very nice built-in for this int. You can just say make adder an int. Except in this case, it needs to be, adder itself right now is a hex representation of it. So we need to say parse adder as a hexadecimal number. And this will take care of the leading 0x for us as well, and we're just going to store that back into adder. Let's just print this out really quickly and make sure that I didn't mess anything up. This looks all right. Let's just hex that really quickly. That looks valid. Again, I can just sort of look at this leading 7f and say that's probably right. These lower bytes are going to be changed every time, but leading 7f says I probably got that. We didn't fail to parse, so that all looks good. And so now we can just pass this p64 the address that we just parsed out. So at this point, it should be good, right? However, I'm sure a number of you, when you ran this, it doesn't work. We get this got EOF while reading an interactive, which basically just means the program's crashed. But we have every reason to believe that it should have worked. So why isn't it working? Well, let's attach to this. Let's gdb.attachp. Let's see, where are we right now? Let me also switch this. So we're somewhere in read and in main. So let's just go down here to the end of main, 400681. And let's just continue until we hit that point. So we're now just about to return out, and this looks good. We are returning to the same address that we put in, or to the same address that was printed out, I should say. Where is it over here? That's not reading it. Oh well. This looks like a valid stack address, and sure enough, pwndebug is showing that this is this looks like good code, right? We're clearing out EAX. We're moving a value into RBX, negating it. This is a trick that some shellcode, in this case, they've opted to use it, where basically this is the invert, the bitwise not of binsh. So you move that in RBX, then negate it to turn that into the string literal binsh. and then push that onto the stack. Then we push the current SP and then pop that into RDI. Basically just say the first argument is the pointer to binsh. And we can work down the shellcode more. But again, this wasn't working, but it looks like it should. So let's step through this and see what's going wrong. So we clear out EAX, we move, negate, push, push, pop, push, and now it dies. You'll notice now that our code is actually changed from underneath us. The instruction used to be like if we start up here at FC80, push RSP, pop, CDQ, push, push, push. However, this is now, if we look at this as some instructions, that's not what it was, right? That used to be some pushes and some pops. Now it's a move, an int3, some weird jumps, a really, really weird add. This is not right. However, so there's a couple of things that we can see going on here, or some ways that we could figure out what's happening. So first of all, the instruction that killed us was push RSP. And of course, pushes are modifying the stack pointer, and they're writing data onto the stack. So the first thing that I would look for here is, where is RSP? Because it looks like, the instructions are getting mangled, so it's quite possible that we're writing data on top of the instructions that we're currently executing. Right, there's no other real way that the instructions can get mangled like that. Something is writing over them as we're running. And sure enough, RSP is this C88, and you can see it's right next to our IP. It's like, within 8 bytes, which is very suspicious. Because this push RSP instruction is only 1 byte. So in theory, the next instruction should be at 7FF FC86. However, when we do this push RSP, that's going to decrement RSP by 8 and then put the contents of RSP into that location, which means that the 2 lowest bytes of RSP are now going to be interpreted as an instruction. Right, because our instruction pointer is now pointing at this address ending in 86. However, we just overwrote that with the actual value of RSP. And so sure enough, if we look at this address as an address, hey, that looks familiar. That looks like, that's RSP, or what RSP was right before the push. So what's happening here is the push is literally just putting new data underneath the processor as it's running the instructions, which is of course not a good thing, right? So how can we get around this? There's a couple of simple things, right? So there's a way we could actually do this without having to deal with this at all. We can actually do some arithmetic on this, and basically, if you think about this as the stack diagram, we can put an arbitrary amount of data in before our shellcode, as long as we make sure to adjust this address to point to where the shellcode is. So we can either just say prepend a lot of data. Let's say SC is, let's add in hex 30 A's, and then put SC again. And now, actually, so so the one thing we do have to be careful about here is we only have hex 28 bytes on the stack to work with. So if we push too much data, then the return IP that's going to be popped off is actually just going to be somewhere in the middle of our shellcode, which is not a valid address to go to. So what we can do here is, well, let's just pad. Let's say we have our hex 28 A's. All 20 of them, so this is going to fill up the stack up to the return address. And then we're going to P64 the address, the base address, plus those 28 A's, plus another 8 bytes for the actual P64 that we're encoding in this instruction. And so what this is going to do is we now have those hex 28 A's, and then we're going to have our 64, our 8 byte number, and then we'll just put our shellcode right after that. And as long as we make sure to adjust that address correctly, we'll be fine. So we'll add our original shellcode, and now all this can just be simplified to sendline SC. So again, sending hex 28As, fill up the stack. Our return instruction pointer is now our address, plus those 28As, plus the 8 bytes from the return instruction pointer, so that we should jump essentially to right where the cursor is here, to the beginning of our shellcode, and hopefully we'll win, assuming I didn't make any logical errors. Let's see, did I do it right? I did, good. So we got shell. Cool. Now, like I said, there is another way to do this though. We can actually, if we undo all of our changes here, not quite that far. Okay. Yeah, so we can do this a different way. So at its core, right, shellcode is just instructions. And RSP is currently pointing to somewhere sort of like just above, it's pointing to the shellcode itself. And so after enough pushes, we're modifying our shellcode underneath us, which is not good. But again, we can put whatever instructions we want in here. So what if we just told RSP to go somewhere else? What if we just like subtracted a bunch or added a bunch to it? In this case, let's just try subtracting some number. Binja, actually this is a good time to point out Binja's thing. If we create a new just hex thing, Binja has they have an assembler in the program. So we can just say assemble sub RSP hex 40, I don't know, some number that'll be enough to get us through all the pushes. I think that should. And it'll give us the corresponding bytes. Cool. And we're in hex, so we can literally just copy this all as an ASCII escaped string, and literally just drop that into the beginning of our shellcode. And there was an at there. So our shellcode is now subtracting 40 from RSP, and then running all the normal shellcode, the like stock standard shellcode. Radare also has a command line utility for this called RASM2. So we can say 64-bit and then do the exact same sub RSP x40, and it probably gives us the exact same output. That looks about right. Yeah. So regardless, this should also work. Again, in this case, we don't need to change any of our offsets because all of our shellcode is still just at the very beginning. Like all of our shellcode starts at the beginning of the buffer. We didn't do any weird padding stuff. So we can just subtract that amount. And in theory, again, assuming I did this right, yeah, we have a shell again. So multiple solutions. If it hasn't become obvious by now, a lot of challenges will end up having multiple solutions as we get kind of further and further into pwning. You know, programs are complicated. There's more than one way to make them do what you want. So, all right, that's cool. Let's take a look at backdoor. Not backdoor. Let's pull up the pwnable from that was due today. If I can find it. Oh no, that was backdoor. Wait. Oh, let me actually just take a look at Labyrinth really quickly because I wanted to point out a couple of things in Binja that I guess we didn't mention that make this problem a little bit easier. So we're in main. Let's go into, we are in GraphView, which is big. Okay, so I got a few people who are a little bit confused about what this rep stos cube thing does. I believe we mentioned this as some like the fun that x86 can do. Rep is a prefix that basically just says repeat. So what rep does is it basically it decrements ECX, it uses ECX as a counter basically, and then repeats this instruction or repeats this stosq that many times. So in this case, this is doing a repeat store, and it's basically saying store rax, which has been initialized to 0 here, into RDI. RDI is automatically incremented by 8 for each repeat as well. So this is effectively just a memset 0, where the length is determined by hex 10 keywords. So 80 bytes total. But yeah, actually, was this, Josh, was this literally just a memset that got compiled into that, or was that?
It's the equivalent of memset. It's
But you did like a for loop or something?
no.
Oh, okay.
It is C's static initialization.
Oh, okay, okay. But yeah, so
equals open curly 0 close curly.
okay, yeah. So this is effectively a
But
memset.
memset can also
Yeah.
do that.
So yeah, so hopefully that answers that stuff. You probably, so like Josh said, this got omitted because if you have like an array in C, you can do blah 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 equals curly bracket 0, for example, to initialize all of them to 0. That's what this got compiled to. Since we're compiling all these without any optimizations, in theory, if we had actually used memset, that would have actually been a call to memset. But anyways, to clear up, that is just zeroing out memory. And then yeah, so we're trapped in a windy loopy something, windy loopy maze. Okay, and call f gets on something to get input, and then our main function is this traverse function, which it looks like if we did it wrong, we get eaten by a GRU, and if we did it right, then we made our way out and we get our flag. So traverse. Let's take a look at some of the things in here. This is mainly just to point out a particular feature of Binja. So where's our symbol of? I'm walking over it. Was the actual initialization here? No. Okay. Let's go into linear view then, and somewhere down here there should be the symbol for a. There it is. Yeah. Okay. So eventually, with reversing, you'll see that we have this. We have all of these different things, A through J, and so one thing that's good to get used to is not only figuring out what these look like through code, but also just like when I look at this, I can see okay. So obviously, these have been padded out, right? Because these are all zeros. So in theory, the D words here are all zeros. That probably isn't actually a data field, especially because it stops early at J, right? This is probably just padding, which is what C compilers do to make things a little bit more optimized and keep things aligned nicely, but whatever. And then you can see we have 3 keywords in here. Because we have E3 and then zeros, F901 and then zeros. We don't have any data starting at these bytes. So these that looks like a keyword. So if we hit D 4 times, we'll turn that into an int64. And then, like I said, one thing that's good to get familiar with is on 64-bit, your programs, with very few exceptions that we'll talk about sometime later in pwning, code always starts with this 40 in the 3rd byte, and your static data and GOT and all that always start with 60. That is just how they're always laid out by GCC. So what I notice here, though, is I see a lot of these 6010, and if we look at where we are, 6010, these look like pointers, right? These look like pointers to some other data in this cluster of nodes. And if we, again, hit D 4 times on that to turn it into these data, we can see, if we double click on that, okay, so that's like a pointer to C, this is a pointer to G. So that looks good. This looks like a pointer to some data type. And we see we have this gets repeated, right? We have this same sequence of in 64 and 64 and 64 all over the place down here. So as if you've programmed in C before, you'll probably realize that these are structs. These are groups of data that are treated as a structure, as a sort of like a class. They're just chunks of data that are represented like this. So sort of recently, not super recently, but also it hasn't been around for all that long, Binja got the ability to create your own types and your own structs in this struct view. And again, down here in the bottom right, where you can get to the hex editor, disassembly graph, strings, all that, there's the types view. And if you're in this view, you can just right-click and hit create new structure. And so we can say, we don't have a great name for this yet, so let's just call it like a node, right? It looks like you're doing some kind of traversal, but it could be a tree, it could be a graph. We don't really know. I haven't looked in to see if it's if it's cyclic or not. So we'll just call it a node. And we know it's 3 keywords. So we know that's going to be 24 bytes total. So we create that. And now what we can do is we can use D again here, or Y, sorry, to create a structure field. And this is basically just saying, the first some number of bytes of this struct is this thing. The next 2 are this other type, and we can name them and all that kind of stuff. So this first one, it was a 64-bit number. So you went 64. You could also just say an int 64. It doesn't really matter. And this was just some number, so we'll just call it num. And you can see now at address 0 we have this uint num. But these look like pointers. So what we can do is we can actually say these are node stars, and let's just say, well, I'll drop now that it happens to be you enter L or R, so let's say left and right. So this is node star left, and this is node star right. Right? So this now looks like a good definition. This pretty well matches what we've observed in the data. So if we go back to, let me go back to linear and A, so we can now say that this data here, by hitting Y to change the type of the variable, we can say this is just a node, and Binja will automatically reparse the data into the nodes that we've defined, and it'll even say, hey, since this is a node star, I'm going to realize that's not an address, that is another node, so it'll name these for us. And so we can do the same thing here. The same thing here, and the same thing here. And so you can see pretty quickly this dissolves into, it looks like some kind of graph, right? Because we see G twice. And so if we, once we go through a little bit more reversing, which I want to get to the last pwnable, so I'm not going to do a whole lot more reversing on this, but basically what ends up happening is you need to find the correct left-right input string, such that when you traverse this graph, the nums of the nodes that you've visited sums to the correct number, decimal 9595, I think. And so yeah, so structs are a great way to kind of more visually see data and get closer to the original C representation. One other thing I did want to point out. In Traverse, we can also, not only can we kind of figure this out based off of how the data is stored statically in the BSS, we can also figure this out based off of how the data is used. So in this case, we do a compare, and again I'm hitting R to change these into ASCII, into letters, to characters. So we compare AL, which in this case is just again, it's the current index in the string that we're looking at. And if it is L, then we're going to take RBP minus 8, which is this constant, which happens to be, there it is, there's the beginning of the node. So we can also just say display that as a pointer to tell Binja, hey, this is actually not just the magic number, hex 60, whatever, this is actually A. So RBP minus 8 is the pointer into the element that we're currently working on. And you can see now that we've told that that's a pointer, it's automatically actually inferred that RAX plus 8 is node left and RAX plus 10 is node right. However, if we don't have, we already have these annotations, so say we didn't have those, like a telltale sign of structs with this is you'll see this kind of, usually in loops a lot of time, right, because you do a lot of traversal stuff on, they basically have to be structs. And so you'll see this kind of, it's hidden under my cursor, you'll see some base plus a constant offset plus an offset in a loop or something like that. And especially in this case, since we then move the value, like, right, we notice that we're dereferencing it. We have brackets around this. So we're taking RAX plus 10, getting the address there, moving that into RAX, and then taking that and putting it into what is essentially our current node, right? So this is definitely looking like some kind of traversal. And so these look like pointers, and since they're all in line with the data, it makes the most sense to say that's a struct and it's not doing just some weird arithmetic to, like, you know, in theory this could actually just be a sequence of number pointer pointer 0, number pointer pointer 0. It could be that. However, it just makes the most logical sense to say that this is a struct. So yeah, in this case, the main thing that I wanted everybody to get out of this is just struct stuff, because it can really help your annotations just automatically. You know, just by creating that struct and saying we're starting at A, this will automatically tell us, okay, this is now, if you're going left, this is telling you exactly what you're doing if you're going left, and if you type R, this is what you're doing if you're going right. You can see where left and right are used, and it just makes disassembly a lot easier to read. So that's why I wanted to get out of Labyrinth. I don't actually care about that. And one last thing that I wanted to go over was backdoor. So this is the one that was due this week, if I remember correctly. Yes, okay. But check out my shell commands. Okay, so again, we see gets. Again, this is a good sign. However, this is probably one of the last weeks that we're going to be dealing with gets, because again, stack cookies, unless you're in a fork accept server that you can brute them on, basically prevent all of these attacks. So sorry, but we still have it for this one last time. So this is, you know, again, just something to note. But we get into this var28, so we can override RIP again. We don't have any cookies, which is good. However, where do we jump to, right? We don't have, if we open this up in GDB, was it backdoor? And we check sec on it, you can see NX is now enabled. So we can't just like jump to our shell code again. And even if it was disabled, we don't know where our stack is, again, because we don't have a leak and it's randomized. So what can we do? Well, we do have this getTime function. And, you know, this so we have a constant here, we've got bin date, we're moving that into EBX, and then we're doing this compare on two immediates, all right? This is never going to be true. This, with any level of optimization, this code would have been completely thrown away, right? Because dead is never equal to lead. However, since it's still here, perhaps we can use this. So in this case, right, whatever ends up in EBX at the end of all of this passes the first argument to system, right? So we really want binsh to be in RDI to get our shell, because bin date is just not, it's cool, but like it's not useful. So but how can we bypass this check, right? We're comparing two immediates effectively. This is not a thing. But what if we just like bypass the check, right? We can jump to anywhere. So what if we just jump to here? What if we just jump to where we set EBX to binsh, right? The only thing that we're going to be missing out on is our stack stuff at the top. However, it probably won't matter in this case, right? Because we aren't actually doing any stack operations after that. Everything is done in registers. So even if we're overwriting data, and even if we were doing stack operations, we're just going to be like clobbering the old function stack frame, which is fine because again, in theory, if we do all this correctly, we'll have our shell. We'll be done with our shell by the time it gets back to the old function. So we don't care anymore. You know, the program can just destroy itself for all we care after we have our shell. That's all that matters. So let's just try that. Let's just try directly jumping instead of jumping to the top of getTime. Let's just jump here. Let's just jump to where we want it to be. So 4006 BB. This is a good time, I guess. So, you know, as I said earlier, Buffin, not that. Or I guess it wasn't Buffin. Either way, sometimes the places you're going to want to jump to aren't going to be symbols. So this is a great example of that. You know, there is no symbol pointing to this address, so we're going to have to manually put that address in. In theory, you know, we could say get the address of get time and then manually add an offset, but why? It's the exact same as just hard coding the number here. So let's actually just copy Boffin because it's got the like the pwn stuff that we need by default. Boffin, this is now going to be backdoor. Let's see, did our stack change any up here? Nope, exact same. Subtract hex 20, and then we also push RBP, so it's 28 effectively. That looks good, so 4006BB. All right, and let's try it. Okay, well, it didn't crash, and we have a shell. So this is kind of a good. This is a very good primer for when we start talking about ROP next week, because one of the premises of ROP is basically, well, the functions that we ROP with are not functions. They're little snippets of functions, or really even just sequences of bytes even that are executable that do the little things that we want them to. And this will, you know, we'll explain all this really in depth next week. But the idea of maybe we don't need to jump to the function, maybe we can just jump to the instructions that we want, right? This is also sort of like shellcode stuff where I'm sure the shellcode didn't have any like proper stack frame set up, right? It just messed up the stack however it wants because again, as long as we have once we get our shell, we don't care what happens when we return. So as long as the stack is not going to get corrupted underneath us, we don't care what we do to the stack to get binsh running. And in this case, again, no stack operations are actually even done here, so it doesn't make any difference whatsoever. We can just say jump here and just run the 4 commands, and we have our shell. So that's backdoor. That's all the pwnables for the past 2 weeks. Does anybody have any questions about this or the prior to or reversing? I should have taken a breather after the end of reversing, but forgot to. So, any questions?
Ask questions now. It's going to get harder.
Yes, like Danny said, it's only going to get harder from here. So if something doesn't make sense here, do ask questions, right? No shame in that. So, okay, if that's the case, then I'm going to run through the web one, I guess, really quickly. That was due this week. Go here for shell. Right. Yeah, so apologies again that the shell broker is still slow on the web ones. We still have no idea why it's slow. And at this point, we probably won't have any more web challenges until the final, so I don't think we're going to spend time to fix it. But, so once it loads, we're presented with Mr. Elite Hacksaur's blog, which unfortunately, if we just kind of do a little bit of recon and wait 10 seconds for the page to load, well, unfortunately, Elite Hacksaur's blog has been wiped after a hack. So, okay, what can we do here though, right? What's our attack surface on this site? Well, we have this nice big green login button that looks very interesting. And this entire time, if you can read it up here, we've been navigating around all under index.php, but with this page equals login, or page equals about, or page equals welcome, I believe was the last one, and autofill. Yeah. So, yeah, this is what we have. We need to log in. So let's just try some basic SQL injection. Just or 1 equals 1. And let's just mash on the keyboard a little bit for a password. Do we get anything? No, no such user. Well, that's rather unfortunate. So we could spend a little bit more time working with SQL injection. However, usually, so the way I usually do web challenges and CTFs is you usually want to give each like attack vector that you see a quick glance to see, just like, can you just copy and paste some snippet in to see if it's exploitable? In this case, our copy and pasted SQL injection did not work. So let's try like our copy and paste injection, seeing that, hey, this looks kind of weird. Like I believe we had a challenge on this week 3 where we could do some injection into this potentially. And just to confirm, we suspect that these pages being included are login.php, for instance, and sure enough, if we go to login.php, we get content back. So we know that site actually, or we know that page actually exists. So, as I have handily prepared, we can go to the convert base64 trick that we talked about, where because lol PHP, you can include basically stream filters. So we can include login.php base64 encoded, which means we're just going to try and include a string, which again, because lol PHP, that's just going to dump it out to the page. Right? Why would it not raise an error or something saying, hey, that's not PHP? No, it's just going to dump it out to the page. One other thing I do actually want to just say really quickly. So, like I said, and like we saw, if you go to /login.php, you'll see that there's content. However, just page equals login suggests that .php is being forcefully appended to whatever query we put into this page, which is, again, very common because otherwise you could use this to read arbitrary files off of disk, which some CTFs do have a challenge, which is literally that, where you can include arbitrary files off of disk. However, in this case, we have just something .php which is included. However, what's nice about the filter trick is that .php will still get appended to this, that's actually what makes this valid, right? Because the resource that we want is not just called index, it's called index.php. Or sorry, the resource is called login.php. So if we wait again some seconds for this to load, hey, we get some base64 back. This looks good. So let's take all of this, make sure I copied it, looks good. Let's open up terminal. Go blah base64, and I'll make that bigger in just a second. Okay, so we have our data. Is that big enough to be readable-ish? Looks good. Okay, so our decoded stuff. This is really all we care about. This top PHP. Let me shrink down the window a little bit. Oh, that's right size. Okay. Because everything down here, right, the only PHP that we see down here is just this isSet error, then just printed out, which is how we get that no such user message out. This is like the bulk of our code, and this is another standard thing with PHP, is you'll usually see kind of all of the processing code that needs to be done on the page at the top, and then if you get any errors back, you'll just echo those into the page as they come up later down here. This is primarily done so that if you're, if you have, say, like when we're logging in, you can directly just set a header and redirect them without having to actually do what I did here, sending back some JavaScript to redirect them. The reason I have to do this is because I was using templates, and so there's actually data sent back already, so we can't modify the headers. Regardless, what do we see here? SQL, right? But this is different. We see this bind param, execute, and bind result. Bind param, if you look at the PHP docs, or you can almost just kind of guess based off of how it works, we have this prepared statement where we have question marks instead of our actual content. And I believe I mentioned this probably week 1. In MySQL, you can do these kind of prepared statements where you basically send the query along and then afterwards send the data. And that basically defeats all, or I think it does defeat all first order SQL injection bugs. which means we're not going to have a lot of success trying to inject into this, regardless of what we do. So, yeah, that's unfortunate. And there's not really anything else here. However, one thing to get very used to for CTFs is reading comments, right? These sites have been written specifically for this challenge. If there are comments, that is the challenge author telling you something that you need to know. Oh. No problem. So we see two comments here. We see this allow old accounts that still have plain text password as well as new SHA-1 accounts, which doesn't seem very useful right now because we're still doing, this is still doing a strict comparison, right? We would still have to get the password exactly right. However, we also see this. Again, playing into the meta of the site was hacked and the owner had to restore from this. They say they restored from this db.sql file. So we have a way to leak files. Well, we have two, really. We have this filter include stuff. However, as we said before, this forcefully appends .php to the end. And there's not really a way to get around that. So what we can do, though, is, web servers serve you files. And in this case, I probably should have explicitly said this was restored from var www db.sql. However, in this case, let's just try going to /db.sql, and after a second, we should get a download that pops up. Excellent. So, I don't want that. So we now have this SQL file. That's way too small. It's not large enough. So this was, I guess, the one leap that you had to make in the challenge. Again, we had two ways to leak files, one of which definitely couldn't have worked. This was not under subdirect or anything, so why not throw out a couple extra requests to see if you can find it. Again, just kind of playing into the CTF meta. If you see specific files mentioned, you're probably supposed to get them at some point. The one exception to that would usually be like a config file or something that has the flag directly in it. Usually it's not as simple as just include flag.txt. But regardless, we have a SQL file out. And for those who don't know, all SQL files really are just a sequence of commands that the SQL server should run. And in this case, you can see this is recreating all of the database. They're recreating the database, recreating tables, and the data in the tables. So we have this admin account with correct horse battery staple as the password. This is where this part comes into play, though, right? If this was SHA-1, the data in the database would be a SHA-1 hash, which you can, there's not an easy way to reverse them, right? You have to either do some kind of brute force or just hope that Google's cached an answer from some forum or from somewhere else. But in this case, we're allowing both. So we can just enter this directly. We don't have to do any password. We don't have to do any brooding or anything. And we can move on to the next phase of the challenge. This was also different from some of the other homeworks because this was not just a one bug to win challenge. You had to do multiple things. And yeah, anyway, so admin password that we got from the SQL file. And once it loads, we're back. Well, one more time. There it goes. Okay, so now we're back at our welcome page. And if this window was smaller, it would be much more obvious that admin had appeared. So we now have access to this admin page. And if we go there, okay, admin panel for the blog, great. This is always a good position to be in. So this is not useful, right? We can't interact with that at all. However, we have this file upload to upload media to the site. So this was one other place where you need to realize how PHP works, or how Apache and web servers interact with PHP, I guess would be a better way to put it. So any content that ends in .php will be passed through the PHP interpreter before it's returned to the user. So you can put whatever you want in a file, and PHP will interpret it as long as it ends in .php. It can be in any subdirectory, as long as there's no other rules saying don't do that. You can put whatever content you want in the .php file, and PHP will interpret it. So in this case, this is great because, well, we can use this leak to also leak the admin page, which let's do really quickly. You could also in theory you could also leak the admin page without having logged in. However, you still can't do anything with it, but there is no protection on that. So echo blah. That's not how you do it. Okay, so now we have this, and if we look at the source for this, you can see we do check to make sure that the user is authenticated as user ID 1, which is our admin account. But after that, if you've posted something, we just save it straight up into the uploads folder. We don't do any extension checks. We don't do any file. We don't do any content type checks. We don't do anything. We just drop it into uploads. And this is where, again, you realize how PHP works. Well, we can just upload a PHP file, right? We can just upload whatever file we want. So let's create a nice PHP file, a very nice one, that says echo system. This is the one that I always use for these types of things. Just breaking it down, there's arbitrarily large number of ways to solve this challenge once you're at this point. I like this one because this will basically give you a shell, right? It's going to take the output from calling system on whatever command you specify in the URL and just kick that right back out to you. So you can do whatever you want with this. And assuming, let me make sure I didn't typo anything, looks fine. If we now go back to our admin page, we can just choose this PHP file, upload it, and shortly it should reload. And so, again, I was nice here and I just gave you a nice little link to it. So we're here, and now it's blank, right? But this is sort of to be expected because our script returns the output of system of whatever we tell it. So let's say command is ls. And in theory, we should get the output of ls. Good. In this case, I actually guess I didn't need the echo. It looks like it's duplicating things. But at this point, I believe a number of people actually got caught up on this part. The flag is at /flag, not ./flag. So there you go. Just cat /flag. You could also have just made your script echo file get contents of /flag.txt. So this should also work. Or I think you could also just include flag.txt. I believe that also should work. So yeah, okay, we got a thumbs up that works. So yeah, this was to kind of teach a couple things as well as make sure that everybody retained the few injection things from week 1 or week 2 or week 3, somewhere in there. But yeah, file uploads are great if you haven't found that out already. And yeah, does anybody have any questions about that challenge? If not, then it is 8:20, so I believe we're going to call that a day. Homework for this coming week be due normal time. We should be back on a normal schedule for a couple of weeks at least. Homework should be up within a couple of hours once we get dinner and, yeah. So anyways,